Hello there, this is Burek from the Joy of Sailing channel. Just came back from sailing a couple days ago. Spent a few hours sailing on Kent Lake with another student and our instructor. The weather was great, not too hot, low humidity. The wind was also good, not too strong, just a few puffs and gusts here and there. But other than that, we had a great time, and as it is always a great feeling to go out on the water and steer the sailboat. So I think at this point I'm ready to take my water test for the level 1 rating. But in the meantime, I have been looking forward to the level 2 program that also includes marine navigation. So I have been spending time researching on that on the internet, and I found a few good websites. The first one I ran across was this one by Nick Nolan, who is a Coast Guard and a rated navigator. It is called Celestial Navigation Video Series, and as the name indicates, it's a series of 12 videos in total that cover the basics and more advanced topics in celestial navigation. I would highly recommend this video series because at least I myself was able to learn a lot from it. Now, if you are looking for something more structured and formalized, you might find this website helpful by Vanderbilt University. This is the astronavigation online course, which is freely available if someone is interested in taking it. You don't have to register or anything like that. You can just go to this website. So feel free to post a video and just take down the link at the top there. And you can go to this website and again go through all those classes. There is several of them with the increasing level of difficulty, but it covers some basic stuff like coordinate system and then how to plot your position on the navigation chart, and it even includes a neat sight reduction table for calculating your estimated position, but more about that in the future. And if you really want to dive in and learn about the history of navigation and learn about the nuances and all the details, I would highly recommend this website, which is the Wikisource, based on the famous navigation textbook by Bowditch, American Practical Navigator. It's got all 37 chapters, glossary and acronyms, and it makes a pretty good read, although a little long. But I already started, and I think I'll keep going as long as I can at my own pace. But that's some pretty interesting stuff if you want to learn about some nuances and some historical details of how the concept of navigation has been developed throughout centuries. Actually, this makes a pretty good read. But for the starters, I thought of something more easier and simpler would be a better thing to do before we even start diving into those more advanced navigation concepts. I think that a good topic would be apparent noon at local meridian. So in some situations you would like to take the noon side for the sun, so you would like to know precisely when the sun is going passing over your meridian or going right over your head. And one might think that this should be at 12 o'clock on your watch, but it isn't always the case. Actually, that is rarely the case because there's multiple time zones on the planet, and even in the United States there's like 6 different time zones. So you need to know what the time zone is and when the standard meridian for the standard time zone is, and you need to know your time as well and the GMT time to be able to determine the exact time or moment of the sun's passing over your local meridian. So I think I was able to boil down the whole process to 4 steps. The first one being just guessing your position, your current position, which is also known as dead reckoning, and that it's really the best guess as to what you think where you might be, and there are some ways to estimate your position, but we'll talk about a little bit more soon. The next step is to know your standard time. You have to know in what time zone you are, or you need to know the universal time, which in the first approximation is the same as Greenwich Mean Time. Then you need to know the equation of time for the day of the year, when you think you will be taking the noon side for the sun, and based on that information, we should be able to calculate the exact time of high noon at our local meridian. So the best way to learn is through example. So let's take a look at a hypothetical scenario. Let's say that we are sailing just south of Sanibel Island, and we have been able to determine our dead reckoning to be 82 degrees and 5 minutes west longitude and 25 degrees and 22 minutes north latitude, and the date is 4th of July and the year is 2017. So this red vertical line represents our local meridian, which is in general not the same as the standard meridian for our time zone. You can also see on the map the compass. By the way, this is just a section from the navigation chart that's available freely online, and I can include the link to that below. But you can also see some topographic elements and some marine navigation elements as well. So you can see the Point Hebel right here, and some buoys as well there. If you want to know what it looks like, here is the lighthouse at Point Hebel. That's what it looks like, and this is what the if you stand right at the foot of the lighthouse and look due south, that's what you are going to see. So our sailboat is going probably somewhere in this area. So you can use the navigation chart and the various markers to determine your position as well. But for the sake of this exercise, let's assume that you want to rely on the noon side for the sun to be able to do that. So we have to calculate the exact moment of passing of the sun over our local meridian. So let's take let's take a look at the bigger picture of our problem. So we can see the coordinate system and the grid, with the meridians going east from the prime meridian at Greenwich, going east and west, and they go from 0 to 180 degrees west, and from 0 to negative 100 degrees east from the prime meridian. And you can see the parallels that go north and south from the equator, and this red polygon is our standard time zone. Somewhat hypothetical, but it's pretty close to what the Eastern time zone in the United States is. But in summer, it is corrected by 1 hour. So normally it's standard Eastern Standard Time Zone is GMT minus 5 hours. But because we are in daytime daylight saving time zone, it's really GMT minus 4 hours, which is represented by this orange line. Normally it's more or less in the center of the standard time zone, which is this red line, and we are located somewhere here, which is right on the borderline, on the west periphery of the standard time zone. You can also see the geographic position of the sun, which is just a projection of the sun onto the surface of the earth along the line connecting the sun and the center of the earth. And you can also see the GMT offset for the standard meridian of the standard time zone. And for our position, for our local meridian, we'll have to calculate the increment, the longitude increment from this GMT offset to the geographic position of the Sun. So if you are precisely on the standard meridian for your time zone, for our time zone, which is GMT minus 4 hours, the calculation is straightforward. You just need to calculate the GMT offset, and that will determine the time of the noon and local meridian, which is going to be just noon, just 4 hours later after GMT at the prime meridian, plus the correction for the equation of time. So let's take a look at that. How would you approach the calculations for that? So our standard time zone is EDT, Eastern Daylight Saving Time Zone, which is GMT minus 4 hours. The date is July 4th on 2017. Of course, the GMT offset is negative 4 hours. So the standard meridian for our EDT is 360 degrees divided by 24 hours gives us 15 degrees for every hour of rotation of the Earth. So 1 hour corresponds to 15 degrees of Earth's rotation then. So since we know that we are 4 hours behind GMT, we just need to multiply those 4 hours of the GMT offset times 15 degrees, which gives us the longitude of the standard meridian for EDT of 60 degrees west. So the Sun will be passing over, if we just happen to be on that meridian 60 degrees west, the Sun will be passing exactly at noon, at 12 p.m. on our watches, but we need to make a correction for the estimate for the equation of time, because the Earth's orbit is elliptical, not circular, so it has some eccentricity and the axis wobbles. There's a precession, and also the axis of the Earth is tilted. The solar time is slightly different than the mean time, or the time that you have on your watch, and it varies throughout the year. So to be accurate, you need to add a correction for the equation of time, and the way to do that is to look at the equation of time, and it's abbreviated here to EOT, the estimation of time, and it equals the solar time, which is the actual sundial time, or the actual time as determined by position of the Sun, minus your local time, meaning your time on your watch for your standard time zone. So from this you can convert and calculate the local time, because that's what we're looking for, which is the solar time minus equation of time. So where can you get the equation of time from? I normally go to this website, the Nautical Almanac, and if you go to this link, everything you need for 2017, click here. This is gonna take you to this website, and you can find a copy of the Nautical Almanac for year 2017 by clicking on this link right here. I normally go to the regular format, but there's also a compact format, and that's what it looks like. And if you go to page 131, you'll see this is the page for July 3rd through 5th, so there are three days on each page. We're interested in knowing this equation of time for July 4th, so I'm going to scroll down to the bottom of the page, and I can see days 3, 4, and 5. I know it's July 3rd, 4th, and 5th for year 2017. So for July 4th, the equation of time at 0 hours is 4 minutes and 22 seconds. So I know that the correction is 4 minutes and 22 seconds. In July, the equation of time is negative, which you can see on this chart here, because the equation of time varies throughout the year, as you can see, in January, this green line here, this green curve, represents the equation of time. So this red line represents the equation of time. So in January it varies from, it is negative, then let's say from April it goes into the positive territory, mid-April, and then in July it dives under the zero line again, so it's negative, so we have to put the minus sign in front of it. So the equation of time for July 4th, 2017 is 4 minutes and 22 seconds. So now we have to just substitute the values for our equation for the local time, which is the solar time that we're seeking is 12, which is noon. Now we have to subtract equation of time, which is negative in this case, meaning that we have to actually add it. So 12 hours plus 4 minutes and 22 seconds is 12:04:22 EDT, Eastern Daylight Saving Time, or 16 hours 4 minutes and 22 seconds GMT. So this is more or less straightforward if you are on the standard meridian for your local time zone. But what happens if you are not? Because in most cases you will not be on the standard meridian for your local time. So we have to know how to calculate it for a general case when you are somewhere else on some other meridian. So let's take a look again at our example here. We're actually at 82 degrees in 5 minutes west of prime meridian, which is not really 60 degrees. So we're not on the standard meridian for our time zone. So how we approach this problem? Well, we know what the GMT offset is. It is 60 degrees. So we have to subtract that offset from our longitude, dead reckoning longitude, which is 82 degrees in 5 minutes, minus 4 hours times 15 degrees, if we calculated before, which is 60 degrees, which computes to 22 degrees and 5 minutes west. Now we have to convert the time to time, that this is the arc of angle. We have to convert it to time, and for that we can use another table that can be found on the Nautical Almanac webpage, and it's in summary here. It says it's titled Conversion of Arc of Time. If you click on this link, it's gonna take you to this table, and we know that our longitude increment is 22 degrees in 5 minutes, and the way you do it using the conversion table, you just break it down into degrees and then the minutes, and you look up the time for those angles and then just add them up. So for 22 degrees we have 1 hour and 28 minutes. So write it down, 22 degrees, 1 hour 22 minutes. That's the arc of 22 degrees corresponds to 1 hour and 28 minutes in time for the Earth's rotation. And now what we're left with is 5 minutes. So we go back to the table, and in this column, we look at minutes. Under 5 minutes, we see 0 minutes, 5 minutes of angle or arc. We see 20 seconds, 0 minutes and 20 seconds of time. So we just have to write it down, and now we have to add 1 hour and 28 minutes and 20 seconds. So that's our longitude increment. So to calculate the local noon at our dead reckoning's longitude, we have to add our solar time that we are seeking, which is noon, or otherwise 12 hours, plus 1 hour 28 minutes, and plus those 20 seconds corresponding to 5 minutes that were left over, and that computes to 13 hours 28 minutes and 20 seconds EDT, or otherwise 1 hour 28 minutes and 20 seconds PM EDT. So when we see on our watch 1 hour 28 minutes and 20 seconds, the sun is going to be passing exactly over our head or over our local meridian. So I hope this kind of lays out the process and some concepts of the time zones and the local meridian and also the prime meridian, and it kind of helps to understand how to approach the problem of calculating the local meridian and for your dead reckoning. And again, we have to do a correction for equation of time, and we've done it once already, so it shouldn't be a problem now. We just follow the same process, go to the nautical almanac, look up the equation of time. It is negative for July 4th, so to the time that we have previously calculated of 13 hours 32 minutes 13 hours 28 minutes and 20 seconds, we just have to add 4 minutes 22 seconds, which computes to 13 hours 32 minutes and 42 seconds EDT, which, if you have the GMT time on your watch, would be 17 hours 32 minutes and 42 seconds. So this concludes the process and steps for calculating the noon at your local meridian. I hope you find it helpful. Going forward, we'll try to tackle more complex and advanced problems in nautical navigation, and I hope you find it useful, and I'll see you next time.